Well, here we are with Unit 7, Waves, Light, and Optics. This is Lesson A, Waves and Wave Dynamics. Our overall goal in this lesson is to understand the properties and characteristics that are common to waves of all types. And in this first video, we're going to be looking at what are called traveling waves. So off we go. So it turns out that waves are just one of the ways that energy can be transferred from one place to another. Now, when we dealt with mechanics, it's kinematics and dynamics, we put together a particle model. To deal with waves, we want to put together a wave model that we can then use to talk about waves. Our wave model is going to be organized around what's called a traveling wave, which is just an organized disturbance that travels with a well-defined wave speed through space, transferring energy from one place to another. Now, there are two primary types of waves. There's mechanical waves and electromagnetic waves. Mechanical waves are things like water waves and sound waves and earthquake waves. Mechanical waves all require some medium in order for that energy to be transferred from one place to another. For a water wave, the medium is water. For a sound wave, the medium is air. Electromagnetic waves, on the other hand, do not require any kind of medium. They are instead, they're an oscillating electromagnetic and electric field. Essentially, because of electromagnetic induction, an electric field sets up a magnetic field, which sets up an electric field, and they oscillate back and forth and keep each other going, essentially. We're going to focus first here in the first few lessons on mechanical waves, and we'll get into electromagnetic waves later on. So as a mechanical wave passes through a medium, the atoms that make up that medium are displaced from their equilibrium position. This is called a disturbance of the medium. A wave disturbance then is created by a source, like this person tapping the water. When you throw a rock into water or pluck a guitar string, that's a disturbance. Once created, that disturbance travels outward through that medium at some wave speed. Okay? Now, kind of a key point here is that the only thing that moves is the disturbance. The medium itself does not move. A wave transfers energy. It doesn't transfer any material or substance outward from that source. The waves are carrying energy as they move along. You've seen this if you've ever watched a duck sitting on water as a boat goes by, right? The duck stays in one place and just oscillates up and down as that wave moves underneath it. So it's just the energy that's moving through under the duck, not the water itself. The water stays essentially where it is. So there are two types of mechanical waves, the transverse wave and the longitudinal wave. A transverse wave is a type of wave in which the particles in the medium move perpendicular to the direction of motion that the wave travels. So if you shake the end of a string up and down, you're creating a transverse wave. Water waves or waves on a spring or seismic waves, those are all transverse waves. Now, transverse waves are made up of a series of positive pulses and negative pulses. The positive pulses are called crests. So this would be the crest of the wave. And negative pulses are called troughs. That would be the lower down part of the wave, as we see here, right? So we've got the crest there, the trough there. Now, longitudinal waves are waves where the particles in the medium move parallel to the direction in which the wave travels. So here we see like a spring, right? And so if you tap the end of that spring or you push and pull on the end of that spring, it's going to travel in the left to right, and then it's going to compress and stretch in the same direction as that wave motion. Those places where the medium are pressed together are called compressions, where it's stretched apart are called rarefactions. So what's happening here, in these compressions, the medium is becoming more dense there, and in the rarefactions, the medium is less dense. So sound waves are probably the greatest example of longitudinal waves that we'll look at. So both transverse and longitudinal waves can be considered what we call traveling waves. So if you drop a pebble into a pond, the waves travel outward. But we want to know how that happens. How does a mechanical wave travel through a medium? To answer that question, we have to be able to distinguish the motion of the wave from the motion of the particles that make up the medium. The wave itself is not a particle, it's energy. So we can't apply Newton's laws to the wave itself, but we can apply Newton's laws to the medium that responds to a disturbance. For example, let's take this string here. We create a disturbance in the string by sending a wave pulse down it. And we're going to follow one little section of that string. Right here at the front where our dot is in this part, this is called the leading edge of the wave. So as that wave pulse reaches that spot, an upward net force causes that piece of string to accelerate upward. The change in curvature causes the net force to point down. Acceleration, again, opposite to the velocity. So the piece of string begins to slow down there at the top. Then, at the top, there's a downward net force causing the piece of string to speed up in the downward direction. And that net upward force at the bottom causes the piece of string to slow down and stop. So we can see the forces on the string change as that wave pulse moves past that little piece of string. So no new physical principles are required to understand how the wave moves. The motion of the pulse along that string is a direct consequence of the tension acting on the segments of that string. So there may have been an external force required to create that wave pulse, but once that wave pulse starts, it continues to move because of the internal dynamics of the medium. What this tells us then is that the wave speed does not depend on the shape or size of the pulse that creates the wave, how the pulse was generated or how far it's traveled. The wave speed is dependent upon the medium that wave is traveling through. On a string, the wave speed depends on what's called the mass to length ratio. We call that the linear density of the string. All right, so linear density characterizes the type of string we're using. A fat string has a larger linear density than a skinny string of the same material. Similarly, a steel wire has a larger value of linear density than a plastic string of the same diameter. So on strings, wave speed will increase when we increase the tension in the string and will decrease with increasing linear density. So the greater the linear density, the slower the wave speed. The greater the tension, the faster the wave speed. In other media, different properties would affect wave speed. For example, gases. Air is the medium through which we hear sound waves, right? So sound speed is dependent upon the temperature and molecular mass of the medium through which that sound travels. So on a warm day, sound's going to travel faster than on a cool day. Also, the molecular mass of liquids, water, is greater than the molecular mass of air. So sound waves travel much faster through water and even faster through solids. So when we talk about waves, one of the things that we talk about is what's called period. The period is the time it takes for one complete cycle of that wave. So the time that it takes for a wave to come up and back down and then back up again, that's a period there. It's a time measurement, it's measured in seconds. And then we've got something else that we call frequency, right? The frequency is the number of cycles in a period of time. Now, as it turns out, right, the frequency then and period are reciprocals of one another. We also talk about wavelength, okay? The wavelength is simply the distance traveled in one period. Okay, so in this picture here, the wavelength we symbolize with the Greek letter lambda. The wavelength is the distance between one crest to one crest. It's basically the distance between any certain point on a wave and another point at equal amplitude. The amplitude then is the distance from an equilibrium position. So then we have what's called the wave equation, and this governs all waves, okay? What it tells us is that a wave speed, its velocity, is equal to the frequency times the wavelength. It applies to all waves, and we'll use it regularly throughout as we talk about waves. Okay, so that'll do it for our opening video on waves. From here, we're going to talk a little bit about sound and what's called Doppler effect, and we're going to introduce light, then we're going to go into wave dynamics. See you in class.